In this video, let's talk about sequencing using latches and flip-flops. Now, in this video, what we're going to look at is we're going to look at circuits in which the output depends on the previous as well as current inputs, and these are known as sequential circuits. And examples of sequential circuits are essentially finite state machines or pipelines. Now, in many cases, the sequential elements, which are called as latches or flip-flops, are used to enforce a sequence of data. And that sequence of data is known as tokenizing the data. And this ensures that you have less amount of hardware but can process data as and when it arrives. And we need to ensure that any new token does not catch up with an old token that is already in the pipeline. So you need to have gatekeepers, if you will, across the pipeline, which will ensure that the tokens are sent through in a sequential manner. Now, the choice of sequencing, the strategy is intimately tied to the design flow that you're using. And so we're going to be looking at a couple of sequencing strategies in this video. Now, first thing is, let's understand what is timing analysis. So there are two kinds of analysis that can be done for timing. One is known as the static timing analysis, and here the analysis of the design is carried out statically and it does not depend on the data on the pins. The other kind of timing analysis would be doing what is known as a timing simulation, in which you apply a stimulus to the input pin, observe the resulting behavior and verify that it is what you're intended to be, and then advance the timing, change the input pins and repeat the behavior, right? So this is a simulation based, both are simulation based, but here you're actually running the code one after the other and seeing the response. Here you're doing it based on some timing characterization that you've done earlier. Now, what's the purpose of these analysis? The purpose of these analysis is to validate if the design that you have can operate at the rated speed. And typically what we do is we analyze the entire design once, and then the required timing checks are performed on all possible paths and scenarios. Right? So for all input combinations and for all variations, process corners, etc., the design is verified and made, and you need to make sure that in the worst case, the design meets the rated speed. Now, when is a STA done? So the STA is typically done post gate level synthesis. So at the end of the front end of the flow is when STA is done, and it is done to identify what are the critical paths in the design. Right? And before we do that, before we are able to put our faith in our STA analysis, we need to first identify a few things. First thing we need to understand is how the interconnect is modeled. Do we model it as an ideal wire, or as a capacitive, or as a global route with some RC, or do we actually have to look at the real 3D structure and calculate the accurate RC, right? And this would depend on how critical the path is to your system performance. Second thing also we'd like to understand is how the clocks are modeled. Are they modeled as ideal clocks, or are they modeled as propagated clocks, which means there's a skew in the clock, there is a variation in the clock, etc. The third thing also we need to understand is whether signal coupling is modeled or not, because as we discussed in prior videos, in case you have two lines with opposite voltage on them, then it's possible that some sort of crosstalk can be induced on each other, and that can propagate through the route even if it is as a noise. So what's a sequential circuit? So we've looked at combinatorial circuits so far. What are combinatorial circuits? Circuits where the output, every output of this block depends on some or all of the inputs to that block. And if there is a change in an input, then a change in the output occurs after some tau seconds. And examples of circuits would be adders, multiplexers, decoders, etc. A sequential circuit, on the other hand, normally consists of a logical block and some sort of a memory element. And so here every output of the block depends not only on some inputs but can depend on the outputs at some prior instant of time. So we have a concept of what is known as the state of the system, and sequential circuits typically include some sort of a memory and have some sort of a feedback which is built into the circuit. And examples of these would be counters, registers, FSMs, etc. Now, sequential circuits can be further divided into two types: synchronous and asynchronous. Right? So, synchronous circuits are those in which all state variables are an internal state of, or the internal state of the system change synchronously with the input signal. So there is a clock signal, and whenever the clock comes, the state of the system changes every clock. Now, such a circuit tends to be reliable because there is a cadence to when the system responds, and hence it's less prone to failure. And the timing of this internal state is in designer control. So as a designer, you have a lot more flexibility to design the synchronous circuit. An asynchronous circuit, on the other hand, is one in which the state variables can change anytime, irrespective of each other, and eventually can achieve steady state. Now, such circuits tend to be prone to what are known as race conditions, where you have an input and an output changing, and depending on the design of the gate, depending on process, it can so happen that one can be faster than the other. And so in such cases, typically the timing of these circuits is not directly under designer control. Asynchronous circuits tend to be faster than synchronous circuits and generally consume less power because normally they don't have a clock, and clock is a very expensive signal that you normally have in circuits, especially when it relates to power. So asynchronous circuits tend to be used, but they tend to be used less and they tend to be used very carefully. Synchronous is a preferred method of sequencing, especially when you have a clock signal that is used for sequencing. Now, when you want to sequence static logic, we normally use two kinds of elements known as latches and flip-flops. Now, what's an ideal sequencing methodology? That is, what do we want our sequencing elements to behave like? So first thing is, we want to ensure that when such an element is added into the circuit, it does not impact the delay of the circuit, right? That would be the ideal want from a sequencing element. We also would like to have sequencing elements which can be connected back to back, right? So that way, if we don't want to stuff logic between two elements, I should be able to do that. The third thing that the element should do, they should be able to give some sort of flexibility to the designer in balancing what is the amount of logic I can create between adjacent sequencing elements. And these elements should be able to tolerate a moderate amount of skew when it comes to the arrival of the clock. And finally, like with all digital elements, it should consume minimum area and minimum power. So now let's look at latches and flip-flops. And so these are all the basic elements of synchronous circuits, and typically they all have a clock signal. So these elements are going to be always with an input clock, and we're going to look at how these elements change when the clock comes in. Now this clock is going to control the flow of data or the opening or closing of these gating elements. The transparency of the element is going to be controlled by this clock signal. So the elements can either be level triggered, which is the case of a latch, or it can be edge triggered, which is the case of the flip-flop. The edge triggered input is shown with a triangle in the box. So the latch becomes transparent in this case when clock is high. So when clock is high, whatever is at D shows up at Q. However, when clock goes to 0, then Q stays as what it was prior to when clock was 1. So when clock is equal to 0, this gate is essentially closed. Q cannot see any changes in D. The other element is the flip-flop. Now the flip-flop responds or becomes transparent only at the rising edge of the clock. That means only when the clock has an upward transition, Q samples what is at D. Otherwise, this element remains transparent. So this element does not allow changes in D to show up at Q except when there is a rising edge on the clock. Now, what are the characteristic timings of a flip-flop? So again, remember, a flip-flop is an edge-triggered element. There are two inputs, if you will, right, to this piece of circuitry. One is the value D and one is the input clock. And there's essentially one output of the flip-flop, which is the output Q. Now, the flip-flop is transparent only during the rising transition of the clock. So if I look at the timing diagram, say a clock signal comes and this is the transitions at D. So again, in timing diagrams, these symbols denote a transition in the signal, right? So what we have is, to ensure that the flip-flop can perform faithfully or can transmit the data from D to Q, this D, the data signal at the flip-flop, must not change sometime before the arriving edge of the clock. So this time is known as the setup time of the flip-flop. So D must be stable for a setup time before the active edge of the flip-flop. Similarly, D cannot change abruptly once the clock comes in. So D has to remain stable for a hold time after the clock edge has gone in. So depending on where the clock edge is, D has to remain unchanged for a certain time period around this active edge. And this time period is denoted by two limits. One is known as the setup time, which is the time D has to stabilize before this edge comes in, and the hold time, which means the time D has to remain unchanged after the edge is coming. Now, in addition to this, there are few other timings. So again, remember that D is going to go to Q only during the rising edge. So Q is going to sample D once the clock comes in. And so we talk about two timings. One is the CCQ, that is the fastest the Q changes once the clock comes in, to the slowest when the Q changes when the clock comes in. So we talk about a contamination delay from clock to Q and a propagation delay from clock to Q. Now let's look at the latch. Now the latch again has two inputs, D and clock, and one output Q. The latch is a level trigger element, so the output is transparent whenever clock is high. So again, if I now look at the clock signal, D is going to be transmitted to Q whenever the clock is high, else at these points the latch is essentially an opaque element. So now if I consider D, right, and let's assume D is changing somewhere here around the falling edge of the clock. Now let's look at Q and let's look at the various timings associated with this element. Now, when the clock goes high is when the gate opens, right? So when the clock goes high, whatever's at D is going to be transmitted to Q. Now, therefore, there are two timings that exist for when the clock goes high and when the latch opens. The earliest Q can settle down is known as the contamination delay from clock to Q, and similarly you have a propagation delay from clock to Q. Now, when the clock is high, if D changes, then there exists a delay between D and Q. So again, we have a contamination delay which is defined as CDQ. This is the contamination delay from D to Q, and you have a propagation delay from D to Q. So hence, remember, because the latch has two inputs, D and clock, and since both of them can impact the value of Q, you have contamination and propagation delays between each input and each output. Additionally, we need to ensure that the data remains stable before the latch shuts down. right? Because what we want is we want Q to follow D. And because there is a finite delay, D has to be stable for a setup time before the latch closes, and D has to remain stable for a hold time after the latch closes. So again, setup and hold time in a latch are defined with respect to the falling edge in a level triggered latch where the latch it becomes transparent when clock is high. Now let's look at how do we sequence elements using flip-flops. So here I have two flip-flops which are serving as the gating elements, a flip-flop 1 and a flip-flop 2. Both have a clock coming in, and then there is some combinatorial logic that exists between flip-flop 1 and flip-flop 2. And what's the goal of the sequencing? The goal of the sequencing is that this logic must complete processing and have the output of the logic ready before the next input is sent through the flip-flop, right? So we are going to use this logic every time on data as it flows in through flip-flop 1, and we need to ensure that when data flows into flip-flop 1, the previous stage data has flowed out of this logic out of flip-flop 2, right? So these two events need to happen every time the clock edge comes in. Now let's look at the timing diagram. So you have clock, and then you have Q1, which is the output of the flip-flop, and then that output has to pass through this logic and then come up to the input of the second flip-flop. Now if you look at clock to Q, when the clock comes in, Q1 is going to be sampling D1, right? And so there exist two delays. There is a very quick delay, which is the CCQ1, or the contamination delay of the clock to Q in flip-flop 1, or you have the propagation delay from clock to Q in flip-flop 1, right? So the delay from clock to Q is going to be bounded by these two terms. Now, this Q1 is ready after TPCQ1. Once this is ready, this data needs to then flow through this logic. And so therefore, if I look at the input of D2, the input of D2 has to be after Q1 flows through the combinatorial logic. Now this is a piece of digital logic. So again, it has two timings, a contamination delay and a propagation delay. So which means D2 can be ready the quickest after Q1 is ready by a TCD, or the latest after a TPD, right? So again, remember there are two steps here. One is the step from clock to Q, and the second step is across the combinatorial logic. Now, the time period of the clock is given as the time between the two subsequent edges of the clock. Now, what we need to ensure is that in the worst case, this D2 is ready for transmitting out of flip-flop 2, which means that D2 should be ready before this clock edge. Now because this is a sequencing element, this D2 has to be ready for a setup time before the clock edge. So if you look at the longest path from clock to D2, the longest path from clock to D2 is TPCQ1 plus TPD. So that is the latest by when D2 would be ready, right? Now the latest D2 should be ready should be a setup time before the clock edge comes in, which means the time period of the clock has to be greater than the longest path through the logic, which is given by TCPQ plus TPD plus T setup. And if this is violated, then this is known as a setup failure or a max time failure. So whenever we look at any path in sequencing, the first thing we check for is whether the setup time has been met or not, and that is known as a max time criterion or a setup criterion. So by breaking the logic into smaller elements that are clocked, we should be able to use that entire clock period for doing logic. But what happens is that these flip-flops and latches have certain timings that need to be met, and so we need to budget for these times into the clock period. So in other words, the cost of doing sequencing leads to what is known as a sequencing overhead, or we need to budget time for sequencing. And that leads to a reduction in the time available for logic computation. So in this specific case, we looked at the flip-flops. The logic block must be designed such that the maximum delay through the logic block is TC minus this, which is TPCQ plus T setup. So this TCPCQ plus T setup is the sequencing overhead, or the cost of doing sequencing in this fashion. Now let's look at the other condition. Let's assume now that we have the same a flip-flop 1 and a flip-flop 2 with the sequential combinatorial logic between. Now this D2 has to satisfy the hold condition at flip-flop 2. What do I mean by that? What I mean by that is once the clock edge is come, D2 has to remain stable for a hold time after the clock, which means that this path from Q1 to D2 cannot be too fast, right? Because we don't want D2 to change before the hold time of this flip-flop is satisfied. So if we look at this path, the fastest path from Q1 to D2 must be longer than the hold time of the second flip-flop. Now the fastest path we looked at would be the quickest path from clock to Q, which is TCCQ, and the quickest path through the logic, which is the contamination delay. And so this quickest path, CCQ plus CD, should be greater than the hold time of the second flip-flop. And again, if this is violated, it is known as a hold time failure or a min time failure. And you see here that this hold time criterion or the min time criterion does not depend on the clock period. This is purely determined by the times of the flip-flop and the contamination delay of the logic. So what we see now here is that the contamination delay of the logic cannot be 0. It needs to be such that it is larger than the hold time minus TCCQ. So there is a minimum delay that the logic has to provide. Or in other words, if this number is greater than 0, it means that you cannot stick one flip-flop next to a second flip-flop. Some logic has to be stuffed in between the two flip-flops, else you'll have what is known as a hold time failure in sequencing. Now let's look at what happens if there is a skew in the clock. So what do I mean by that? So in reality, the clock pulse has a certain uncertainty. Remember, the path to flip-flop 1 might be different from the path to flip-flop 2, or there can be process variations in the path across the two, which leads to different arrival times at clock 1 and clock 2. And so we'll see what happens because of that. So clock skew determines what is the maximum variation in the location of clock between 1 and 2, which means that if you look at the clock signal, you have one clock which comes, say for example, clock 1 comes in black, clock 2 can come in red. So the edges don't necessarily overlap. The edges clock 2 can either come before clock 1 or come after clock 1. And the maximum variation that can happen between the clocks, we call it as the skew, or T skew is the maximum variation between the rising or falling edges of the clock. So let's look at the case. Suppose clock 1 comes in late and clock 2 comes in early, then we have less time available for the data to flow through the combinatorial logic. So what this would mean in terms of combinatorial logic design would be that we have the clock period minus T skew. So that is the available time we have. It's no longer TC, but TC reduced by the skew, because it can happen when these two clocks are not coming at the same time. You still want the setup time to be passed. So that gives you TC minus T skew should be greater than TPCQ1 plus TPD plus T setup. So to prevent max failure, what you have is you have the logic, the maximum delay through the logic is TC minus TCPQ1 plus T setup plus T skew. So what happens is due to clock skew, you're going to further reduce what is the amount of logic you can stuff in between the flip-flops. So the skew adds on to the sequencing overhead. Now let's look at the other case. Suppose clock 1 comes in early and clock 2 comes in late. Then what we have is that the hold time can get violated. So in that case, you have T hold plus T skew should be less than TCCQ1 plus TCD, giving you a requirement that TCD should be greater than T hold plus T skew minus TCCQ. So again here what's happening is because of the skew, you need to design the logic such that the contamination delay is larger than what it would have been without taking skew into consideration. Now the other way you can sequence logic is by using two latches, right? Now here what we have is so when we do sequencing using latches, we typically use two non-overlapping clocks. So remember that the latch is a level sensitive element. So what we have is we have one clock phi 1 coming into latch 1, a different clock phi 2 coming into latch 2, and then phi 1 comes back into latch 3. So we open alternate gates during phi 1 and phi 2 remains closed, right? So in the previous case we had a flip-flop which was opening only during an input transition, clock transition. Here we now, by using two non-overlapping clocks, we ensure that there's never going to be a direct path between this first latch and the second latch because of this latch 2 which is controlled by a second non-overlapping clock. So what's important here is both these clocks have the same frequency, but they have a certain time which is known as the T non-overlap time. So that is the time when both the clocks are 0. Now let's look at why this will be required. I'll make a case for it. So typically when you want to generate such clocks, the simplest way people generate it is using an inverter. But when we use clock and clock bar, it's not necessary that it will have a non-overlap time. So we have certain circuits which will help us generate these non-overlapping clocks. So they will add on to the total area that is required to do the sequencing. Now we always have L1 and L3 are on the same clock, and the previous combination logic which was between FF1 and FF2 is now split into two blocks. There is one CL1 which is between L1 and L2 and another CL2 which is between L2 and L3. Now let's look at the timing relationships in the latch based sequencing. So let's assume that D changes after the clock, right? So whenever D comes in, this latch is open, right? So which means that the maximum time once the D comes in, when Q will be ready is going to be given by TPDQ1. So TPDQ1 is the time required for the data to go from D to Q. Now the maximum time required for the data to go from Q1 to D2 would be through the combination logic 1 and its propagation delay, which is TPD1. Now remember that latch 2 doesn't operate on the same clock as latch 1. So we have time for this entire data to go through all the way to L3 before the phi 1 gets activated again. So now we have the maximum delay from D2 to Q2. Now the delay from D2 to Q2 is going to be given by TPDQ, or the propagation delay from D to Q of the second latch. And similarly, now once Q2 is ready, it's going to take another propagation delay to get you to D3, right? And so you have the maximum time from Q2 to D3 to be TPD2. Now we need to ensure that D3 arrives at the same time relative to D1, right? We don't want D3 to arrive right at when the clock is rising or when the clock is falling. So to ensure that the sequencing works, we try to figure out the delay between D and phi 1 to be roughly the same as it crosses all phi 1 latches. So which means that your time period of the clock should be greater than TPDQ1 plus TPD1 plus TPDQ plus TPD2. So there are two logic paths it needs to go through and two propagation delays of the gates. So in other words, if I look at the maximum delay I can have through the combinatorial logic, that is TPD1 plus TPD2, it can be given as TC minus 2 TPDQ, assuming all the latches have the same times. Right? So the sequencing overhead in that case would be 2 TPDQ. Now let's look at the min time criterion for this sequencing. Okay. Now what we want is we want D2 to be stable for a time t hold after phi2 is switched off. So remember, phi1 goes high, D1 goes through Q1, comes here, and then phi2 turns on and D2 goes to Q2. Now we want to ensure that D2 does not change once Q2 shuts. So once the clock phi2 shuts off, we don't want D2 to change for a whole time after that. Now the fastest path from L1 to L2 is going to be given by TCCQ1 plus TCD1, right? So that's going to be the fastest for this D to be ready. Right? And we also know that phi1 and phi2 have an non-overlap between the two, which means that we need to ensure that this fastest time plus this overlap should be greater than the hold time of latch 2, which gives you the combinatorial delay or the contamination delay of 1 should be greater than T hold minus TCCQ1 minus T non-overlap. So here is where the T non-overlap helps, because here if you see in a flip-flop, this CD1 was greater than T hold minus some TCCQ. Now because we have this T non-overlap, we can make this quantity to be less than 0. And similarly, I have TCD2. Again, if I look at the path from 2 to 3, I have TCD2 given by T hold 2 minus TCCQ2 minus T non-overlap. Right? And if I assume similar latches, then what I have is that the contamination delays of 1 and 2 should both be greater than T hold minus TCCQ minus T non-overlap. And therefore, the min time criterion can be managed by making this T non-overlap as large as possible. So you can make this as large as possible, and then you can get rid of the min time violation altogether in a latch based sequencing. Now this latch based sequencing provides an additional advantage of what is known as time borrowing. So remember, in the way we have sequenced these latches, alternate latches open up during a clock, right? And so what tends to happen is, because this is not gating, I can take longer on CL2 for CL1 to process, because eventually I need the total time from CL1 and CL2 to be such that D is ready, right? So because this phi2 is opening the latch later, it's not necessary that the logic in C1 needs to be completed while phi1 is high, right? As long as we know that this total, the maximum path from logic 1 and logic 2 is met, we will be safe in the sequencing strategy here. So there is a flexibility in the way we split the logic. We don't necessarily have to split the logic equally. We can tolerate some skew in the logic splitting, and that is known as time borrowing. That is, I can borrow some time from the second logic into the first logic if design needs that. We just need to ensure that D2 arrives a setup time before phi2 goes low, right? And so therefore, if you think about the maximum borrow time, the maximum borrow time should be TC by 2 minus T non-overlap plus T setup. So you have a substantial amount of time that can be stuffed in from the second logic block into the first logic block, or vice versa, right? So this further gives flexibility to the designer in case logic demands that we cannot do these two to be equal to each other. Now, what is the impact of clock skew on the latch based sequencing? Now, with clock skew, again, what happens is, because this latch is open during an entire clock being high, we don't have to worry about the accurate placement of the edge of the clocks, because we are utilizing the level of the latch for transmitting data. So therefore what happens is this sequencing will work for a moderate skew in clock. And this is a very important advantage of latch-based sequencing, is that for nominal skews, this sequencing is tolerant to the clock skew. Right? So we don't need to worry about clock skew. That's not going to impact the sequencing overhead when we're using latches. Now this unfortunately does not have an issue on the max time, but it does impose a limit on the min time. So now let's look at the min time. Why is the min time important? Because the min time, you're dealing with the edge, right? So when you're doing the min time, you want D2 to hold after phi2 has gone to 0. So in that case, what happens is you end up having CD1, CD2, that is the contamination delays of the logics, have to be greater than T hold minus TCCQ minus T overlap plus T skew, right? So this essentially reduces the impact of the non-overlap time, right? So if you have a skew, you probably will need to increase the non-overlap time to ensure that the min time doesn't get violated. And the other impact of skew is that because of the fact that these edges are now moving, it also impacts the amount of time that you can borrow from 2 to 1. And that maximum time that you can borrow is now reduced by this skew time. So now if you think about it, if you keep if you keep increasing the non-overlap time between phi1 and phi2, you eventually create what is known as a pulse latch. That is, you have a clock in which the latch or the duty cycle of the clock is not 50%, but you have a low duty cycle of the clock. So this is known as pulse latch sequencing, in which the clock appears as a series of pulses with a time period of Tc and with a pulse window or a pulse width of TPW. Now let's look at the max delay constraint here. Now what we want is, suppose let's assume that D1 arrives when the clock is high or when during this TPW, right? Which means that D2 should be ready when phi is ready again or when phi goes high again. In this case, basically your TC should be greater than TPDQ, that is the longest path from D to Q, plus the longest path through the logic. So that would be TC should be greater than TPDQ1 plus TPD. Now, if I assume that this window or this pulse width is much smaller than the setup time, that if D1 is ready before the pulse has gone high, then D2 should be ready a setup time before phi p, right? So in that case, what I have is TC should be greater than PCQ1, the longest path from clock to Q, plus TPD plus T setup minus the pulse width of the clock, right? And so what you have is you have two conflicting, or you have two conditions for the clock time period depending on how you choose to place D with respect to the clock pulse. And so therefore what you'd have in this case is your time period of the clock is going to be limited by the longest path between the two, and so TC is going to be greater than or equal to the maximum of these two conditions, and therefore you're going to find that the propagation delay of the logic that you can stuff between these two latches is limited by the maximum of two sequencing overheads, one which is just TPDQ and the other one which is PCQ plus T setup minus the pulse width of the clock. And what you see here therefore is the sequencing overhead is typically just one latch delay if you choose the pulse width to be large enough. That is, if you choose this pulse width to be equal to the setup time, then you're going to see that the sequencing overhead is very small. So this sequencing technique gives you the smallest sequencing overhead. Now let's look at the min time constraint. Now the fastest path from L1 to D2 is going to be CCQ plus TCD. This should not change before D2 can satisfy the hold requirement, which means TCCQ plus TCD should be greater than the pulse window plus the hold time, right? Or in other words, the contamination delay of the logic should be PW plus T hold minus TCCQ. Now what happens when we have a skew on the clock? Now again, if this pulse width is very large, then we have a time over which these two latches are going to be open, right? And so you see some moderate clock skew over which this is not going to have an impact on the sequencing. So as long as the skew exists such that this remains open during the skew, we don't have an issue. So this is similar to the previous case where we had sequencing using two clocks, that there is an tolerance to clock skew that happens whenever we use latches. And so therefore, if you think about the propagation delay because of skew, in the first case, it is limited only by TBTQ, right? And it would be fine. The skew impacts only the other condition when you have the D arriving after the clock has come in. So therefore now the propagation delay reduces to the maximum TPDQ and this particular term. Similarly, you see that the contamination delay is also impacted by the skew, and the contamination delay again increases because of the skew. So the skew is going to reduce your propagation delay, it's going to increase the contamination delay. Now before we close, let's talk about the limitations of static timing analysis. So one of static timing analysis obviously has to be used carefully. You can't expect it to give you answers for all the timing issues in the circuit. So first thing, for example, would be the handling of tri-state. STAs normally deal with logic domains of 1 and 0. An unknown value is treated as indeterminate, so then it leads to propagation of indeterminate values through design. If you have PLLs in your circuit, then the PLL configuration cannot be set up in an STA2. If you have asynchronous clock domain crossings, those cannot be checked because we don't have correct clock synchronizers available. Similarly, I/O interface requirements cannot be checked by STA only. If you have an analog block somewhere in between, that cannot be checked with STA, and so the designer has to ensure connectivity at the analog to digital interface. An important drawback with the STA is the STA can sometimes flag a path that logic will never use because logic may never propagate through the path. And this can happen when an application never uses that path, or if it has mutually contradicting conditions, but the STA does not know that, and so the STA can flag a path and you might be chasing something which doesn't need to be optimized. A FIFO pointer that's not synchronized cannot be optimized. If I have two FSMs, it cannot check if those two are synchronous or not, right? It references the clock. So if I have two FSMs, it can't tell if the clocks are same or what happens at the interface. It cannot detect any issues with clock generation logic or for not matching clock definition. So clock is something which goes as an input. So any issues in the clock cannot be detected by just the STA. And it cannot model any functional behavior that might change across clock cycles. So STA has to be used carefully. Typically sequencing you tend to use STA, but you need to remember that STA will break, especially when it comes to any issues related to clocks or non-ideal digital circuits. So to conclude, sequencing can be achieved using flip-flops and latches. The key criterion would be to minimize the sequencing overhead, especially when we want to meet high-speed requirements. Flip-flops are the simplest to sequence but tend to have the greatest sequencing overhead. Latches are most tolerant of skew and allow for time borrowing, something which a lot of designers like, but they require greater design effort, especially when you want to partition logic into half cycles. Pulse latches have the lowest sequencing overhead but are susceptible to min-time failures. So again, as I mentioned, how you choose your sequencing depends on what is the requirement from your design.